Hi, everyone. It's a pleasure to be here. We had so many exciting talks so far. I hope you guys will enjoy this talk as well. So I'm going to talk about virtual assistants and especially voice-based virtual assistants. More and more people are using voice-based assistants such as Alexa, Siri, Google Assistant. And the reason for this is that they provide a very natural way of communication for us humans. So when a person talks with Alexa, we want to understand their needs. So they either want to perform a task, call someone, set an alarm, play music, get a recipe, or they're interested in knowing, getting some piece of information. But we don't want this to just be any experience for them. We want this to be as natural as possible, and we want this to be a very satisfying experience for the user. To ground things, let's go over an example. So here, a user is talking with MovieBot, which is an Alexa skill developed by my team. The user is asking MovieBot for a movie recommendation. Alexa first asks the user about their needs, in this case, about the genre. The user responds adventure, and then Alexa makes a recommendation. The user can then ask any follow-up questions. Who directed it? Is it any good? Who's in it? Etc. And then they can either accept the recommendation or ask for another recommendation or ask for any other questions about movies, directors, and actors. So here are the 5 components that enable this experience. These are more or less the same for any speech-based assistant. So the first case, like when a user talks with Alexa, Alexa first translates the audio signal into words, essentially replicating our sense of hearing. And this is done by a module called automatic speech recognition, or ASR. Then the text goes through a natural language understanding component, which essentially tries to drive meaning from what was heard. Then we have Dialogue Manager, which says, okay, I understand what you said to me. How should I respond to you? And this really depends on, okay, what have you talked about so far in the conversation? What do I know about you? Maybe I want to adjust what I say depending on who I'm talking to. And then, so I decide, okay, what sort of thing am I going to say back to you? Then we have the application layer, which is essentially your memory or like your knowledge of the world. Says, okay, I know you asked for the director of a movie. I know that what I'm going to respond to is a person's name. So how do I know who directed this movie? I maybe talk to a database or a knowledge base to extract the information, and then I compose the text response. The text response then goes to text-to-speech, or TTS, and an audio signal is talked back to the user. So over the last years, we've come a long way, especially in terms of implementing our sense of hearing and our sense of understanding. But there's still a large gap in modeling our dialogue managers, or essentially how do we decide what to respond to the user. And one thing to note here is that all of this usually happens in noisy environments, so what the user says is not necessarily what Alexa hears or understands. And this is like the same for humans, right? We might not hear what the other person said, but we have a lot of over time, we've developed a lot of different strategies to recover from that noise. Like, I ask you to repeat, or maybe I restate what I think you said. And that way, I can make sure that we're both grounded in the same understanding. So the main problem that is right now the gap is that today's dialogues are written manually. What does this mean? So this means that after, we have developers who say, okay, if I've extracted this sort of meaning from what the user said, how should I respond to it? Should I, make an API call? Should I ask another question? What is the best answer to give to the user for that particular question? But this makes the dialogue design very time-consuming, it's very error-prone, and it's also very limited in the sense that it's hard to develop multi-turn experiences for users. And another limitation is that these systems are non-adaptive, so they don't learn as they have more interactions with users. So our goal here in the dialogue research team is to see what parts of this dialogue management development can we automate. And we want this to essentially like replicate how humans learn over time about like how to respond to users. Humans use their context in order to understand or like come up with the best way to answer a user. Humans also use their history of that they share with you in order to respond to you. Another thing is that we usually like look for visual cues to see if you understand what I'm saying or not, or like should I change what I'm saying, and how can we replicate that? How can we enable our assistants to have the same ability? So going back to the same diagram, essentially we want our dialogue manager to be a learning agent. We want it to be able to get smarter as it has more interactions with users, as it gets feedback from users, and then perhaps even have personalized dialogue managers for the user. So in the remainder of this talk, I will first talk about one way of formulating this problem, and then I will apply that formulation to recovering from errors as an example. Okay, so we can look at a dialogue as a series of interactions, right? So the user says something, Alexa hears what the user says according to a policy that it has, which is that set of rules that I mentioned, a mapping between what the user said and what the answer should be. It decides on the best action to take. And then once it replies to the user, it observes what the user says next, and then it also observes, maybe gets a feedback from what the user said. If the user is happy, it knows that it did the right thing. But if the user is shouting at it, it knows that, okay, maybe something went wrong. How should it like recover from that? So essentially, we can formulate the problem as a Markov decision process, which is composed of 5 components. So we have the state, action, transition probability, reward function, and the discount factor. Let's quickly go over some of these, each one of these components. So first, we have the state, which is the sufficient statistics for the past. What have I heard so far? What do I think you said? What do I know about you? And essentially, all of this is the statistics that I have gathered so far in the conversation. The second one is the action space A, which says, okay, now that I know what I heard, I know what I heard, I know what you meant, I have some information from you, how should I respond to you? And essentially it says, okay, what are the different possible things that I can say to you? For the case of movies, for example, I can make a movie recommendation, or I can ask you to repeat yourself, I can ask some questions for you about, what is your favorite actor, what is the genre that you like, and then, so all of that composes my action space. Then we have the transition probability P, which says if I'm in state S, if I know what you said so far, if I take action A, I decide how to respond to you, what is the probability distribution over the next state S prime? So where am I essentially possibly going to end up in? And this depends on what I heard, what I think you said, and also depends on the user. And because we don't know what the user is going to say, this is not known in our situation. Then we have the reward function R, which says, okay, I thought you said something, I responded to you in a way, and then I ended up hearing what you said back to me. Okay, how good is all of this for me? And this can be evaluated either manually or automatically. Ideally, we want to calculate this automatically, and this depends on different things. Did I give you the answer that you were looking for? Am I getting a positive, so we can do sentiment analysis to see, am I getting a positive response from you? Or are you angry at me? We can look at like voice cues. Are you happy? Are you angry at what I said? And finally, we have the discount factor gamma, which says, how much do I prefer getting a reward now versus getting it in the future? Okay, so now that we have this formulation, the problem that we want to solve is that by observing a sequence of state, action, and reward, okay, how can I find the optimal policy? So again, the mapping between states and actions, that set of rules that I mentioned earlier, such that if from any state I take an action according to that policy, on expectation, I'm going to maximize the sum of my discounted reward. So I'm going to take the optimal action at any state that I'm in. Okay, so having formulated the problem this way, let's see an example of how this applies to recovering from errors. And the reason that we want to do this is, like I said, conversations happen in environments. There might be multiple people talking. There might be background noise. You might be listening to music while talking to your assistant or to other people. And we want to see like how we can actually adapt the strategies that humans have in recovering from understanding errors, and then apply it to machines. So for example, this is another example with MovieBot. So the user asks for the director of cargo. Alexa responds, it was directed by Ben Affleck. The user then says, when did it come out? And then Alexa says, Argo came out in 2012. This is a very frustrating experience for the user, because not that at this point, like, they realize that Alexa heard them incorrectly, but they have to also disregard everything that they've heard so far in the conversation. They don't know if they should trust what Alexa said to them or not. Compare this to an experience where after the user asks for the director of cargo, Alexa says, okay, I think I heard Argo, but I'm not sure. Let me confirm with the user. And then the user corrects Alexa, and then Alexa gives the correct response. So this is a much more satisfying experience for the user. Okay, so what we want to do, we want to learn essentially strategies to recover from understanding errors in conversation. But before we do that, we have to solve a problem. And that problem is that we need a good policy to appeal to users to collect data, but we also need data to train a good policy. This is like a chicken and egg problem, and it's very expensive. Every time we come up with a new policy, go and test it on actual users, because then we might lose their trust, right? We don't want to just try any policy with actual users. And the way that we overcome this is we build user simulators, and we learn a good enough policy with the user simulator. And then once we're satisfied with the quality of the policy that we learned, then we deploy it in production. We get actual users to work with it, and then again, like through that feedback loop, improve the policy over time. So here are 4 components of an example user simulator. First, we generate what the users essentially what the user wants using recurrent neural networks. Then we have the utterance generator, where it says, okay, I know that the user has this thing in their mind that they want. What is the surface form for that? What is the actual sentence that the user is going to say? Then we convert that sentence into audio, and then we add noise to it, simulating different types of noise, different types of environments. And then the noisy audio goes to Alexa. Alexa returns the response, and then in the next turn of the dialogue, the user simulator takes what Alexa said, takes the conversational history that it has so far, and then generates the next turn of the dialogue. So, but it's very important for our user simulators to actually simulate real users, right? We don't want to just like learn any policy and then go and deploy it and see that no, like in production, it actually is not very good at all. So what we did here was we did a user study where we showed 78 participants dialogues that were generated by the user or dialogues that were generated by this user simulator. And we see that overall this was a very difficult problem. 67% of our participants thought a user simulated dialogue was generated by an actual human. And when we looked at the reason that they thought that user-simulated dialogue was actual human, the first row here pretty much sums it up. So on one hand, humans attribute expression of emotions to real humans. If you show them a very bad dialogue, but there's like 2 angry turns there, they say this has to be a human. A user simulator doesn't have emotions. On the other hand, people attribute simple or formal dialogues to simulators, but because in reality, a lot of people are still not used to talking with these virtual assistants, they do use formal or simple language. So again, that was another thing that really confused our people. So now that we have a good enough user simulator, let's talk a little bit about the dialogue policy. So here we're applying the formulation that I talked about to learning clarification policies. So in a very hypothetical scenario, our state is going to be what I heard, what I think the user said, right? What the meaning of what the user said. Maybe I have some sort of confidence over like, okay, how confident am I that the user said this, that the user wants this? And also, what are the previous things what are the previous steps that I have taken in this dialogue? Our actions here are very simple. There are 5 actions. So execute is, I'm going to respond to the user by maybe talking to a backend database. Confirm confirms our understanding with the user. Repeat asks the user to repeat. And repeat intent and repeat slot show partial understanding of what the user said. So I heard Tom Hanks, but I don't know what type of information you want about Tom Hanks. Or I know that you want the plot of a movie, but I didn't hear correctly what movie you were talking about. So the next thing that we need to specify is our reward function. As I mentioned, ideally we want our reward function to be automatic. This is just like a simple rule-based, heuristic-based reward function, but in reality, we actually want to build models to estimate the user satisfaction, to say, okay, how satisfied do I think you are so far in the conversation? And then according to that, I adjust my strategy of how I respond to you. So we tried different RL algorithms. Here, there are the 3 of them. So in the plot here, on the y-axis, we have the return, which is the accumulative reward over the entire interaction. And on the x-axis, we have the learning step. The only thing that you probably want to take away from this diagram is that all the 3 algorithms, they converge to a stable policy very quickly. But this is not enough. We also wanted to compare these RL policies with other simpler policies, like a rule-based policy. The first rule-based policy that we tried was always execute. So here we wanted to understand how important is actually clarification in our dialogues. The second one is that we just learned different thresholds. So it's like a bucketing algorithm based on how confident am I in what you said. I decide what action to take. And then the third approach was supervised learning. So we trained different types of classifiers here. Again, our input is the state. Our output is one of the 5 actions that I mentioned. And then, so we compared these different algorithms in different noisy environments. So here again, on the y-axis, we have the return. On the x-axis, we have the signal-to-noise ratio, which says if I move, like here, if I move from left to right, the amount of noise decreases, right? So at SNR value of 10, I don't have that much noise. This is close to a clean audio, whereas at SNR value of 2.5, it's a very noisy environment. So overall, we see that all the algorithms perform better, improve. They give us more return as the amount of noise decreases, which is natural. Like there's less noise, so you have to recover. There's like less chances that you need to actually recover from errors. So shades of red here are the rule-based policies, and by comparing the 2 rule-based policies, we see the importance of having a clarification policy. So it's not sufficient. People are not, like one strategy that we can take is like, I respond to you, if it's incorrect, you're gonna ask me again for a question, right? But we see here that strategy is not very helpful. And then overall, we see that across different noise levels, the RL algorithms outperform both rule-based and supervised approaches. And then when we look at 2 other metrics, here we have the success rate, and then we have the number of turns to execute. So here it says, how many clarification questions do I have to ask you in order to give you the correct response? And we see that the RL approaches, they strike a better balance. So they don't want to you don't want to confirm after every sentence that the user says, right? But you don't want to not confirm at all either. And here we see that the rule-based and the RL approaches, they get this similar success rate, but the RL approaches give you this by asking 35% fewer questions. So in summary, I talked about data-driven dialogue management and one way that we can formulate this problem. And I talked about one way, again, of simulating the users before actually deploying dialogue managers into production. And here are the people who contributed to this work. Thank you.